Okay, can you finish there, Charlotte? Okay, George, I'll let you know.
Okay.
Hello and welcome back to MSE. It's me, Charlotte, and today we're here with Mr. Barnes and with Laura, our very own Laura from MSE. So do get your questions in because we'll be talking about chemistry today. First off, what's your main top tips for chemistry GCSE?
So in terms of the answers themselves, and bullet point them, basically count the number of marks that are there. So if you've got a question that's worth 2 marks, for instance, the test for an alkene, and you write that it goes colourless, then you're not going to get 2 marks for that. You've got to have at least 2 points in there. So you can be talking about the bromine water going from orange to colourless, so you've got that starting colour as well. If you're talking about the test for chlorine with damp blue litmus paper, and again it's worth 2 marks, then we're looking for that it goes red first and then it's the bleaching after that. So bullet points those and count the marks. Show all the working. If you're doing calculations, make sure you're really clear in your explanations for that. So put units at the end of each bit so you know exactly what the units are. There's got to be 20% or so of the content being mathematical. So that includes transferring units. So be careful of going from grams to kilograms, that sort of unit, that you do label them really clearly. If you've got a question that refers to a table or a graph, so if it says use the data in the table, use the data in the graph, then make sure your answer refers to it, because if you don't refer to it, you won't get all the marks. And the same is true if it asks a question that relates to a particular object. So if you're talking about a material to make a sink basin or to make a pipe, then your answer's got to refer to why that material is particularly good to make that object. Other than that, it's really sort of concentrate on the core concepts. So make sure that your equations are balanced, double check those afterwards. Where you can, try and make sure that you explain each step in your working out and start logically. So if you need to take a few seconds first of all to think through, take a few seconds to think through and maybe highlight a couple of points in the actual question itself to help structure your answer.
Yeah, definitely. So we're getting a few questions in. Abby says, can we have a brief summary of electrolysis?
Ooh, electrolysis, okay. Right, so electrolysis works. Electrolysis is to split, so lysis to split and to split them up into ions. So first of all, you've got to have an ionic compound. So one of the things that's really important to the whole lot of the chemistry is to be able to recognise which compounds are which substance are which. So that means that you know that something that's going to be a metal and non-metal would be ionic. If it's ionic, that means that it's going to have high melting and boiling points, because the 2 ions, the positive and negative ions, are attracted very strongly together in a giant lattice. So you've got to break lots of bonds for that. If you've got an ionic compound, one of the tests for it is that it doesn't conduct when solid, but it does when molten. And it also does when it's dissolved in water. So the first thing about electrolysis is that you've got to have ions that are free to move. So solid sodium chloride won't conduct electricity, whereas sodium chloride that's molten will, and sodium chloride dissolved in water will as well. Once you've got that bit and you've sorted out that conduction is going to happen, then you need to have a think about how that works. So you've got a positive electrode and a negative electrode. Opposites attract. So the positive ions, they're the cations, because they're positively charged, so cations, and they are attracted to the negative electrode. So the positive ions go to the negative electrode. And then the other thing to bear in mind is that the products are going to be neutral at the end of it. So your positive ion gets attracted to the negative electrode, and then that positive ion becomes neutral. So it gains electrons. So the positive ion gains electrons, and that means that you've got a reduction reaction taking place. Remember, if you always see metal extraction, that's always down to reduction. So the metal ion gets attracted to the negative electrode where it gains electrons. On the other hand, your negative ion, your anion, gets attracted to the positive electrode, and it loses electrons at that point. And then that's where we have our oil rig. Oxidation is the loss, so that happens to the negative ions. They get attracted to the positive electrode, whereas on the other side we've got a reductionist gain. And we can write that as some equations. So if we've got, for instance, sodium chloride, then I've got sodium made of this positive sodium ion over there. I think we got that on the board. Okay, well, we're going to pop that on the board in a second, hopefully. So my sodium ion gains electrons, and then it becomes sodium like so. This is in the molten state, so here I've got the liquid, and there I've got the liquid as well. On the other hand, the chlorine has got a negative charge. That goes to give me chlorine like so, and chlorine exists as a diatomic molecule, so that's Cl2 over that. And then to balance it, I need to have 2 over there. Each chloride ion has got 1 electron. I've got 2 chloride ions that lose electrons, so I can put 2 electrons over there. You might see it written as slightly differently. You might see it written with the -2 electrons over there. That's the same, -2 electrons on one side, plus 2 electrons on the other side. If you've got the liquid, so if you've got the molten, I should be saying molten substance, then you always get the metal and you always get the non-metal formed at the end of it. So the sodium metal gives you sodium metal ions, will give you sodium metal out at the end of it. The chloride ions will give you chlorine gas at the end. The bromide ions give you bromine gas out at the end. The difference comes when you do solutions when you start dealing with the solutions, because sometimes you get, instead of getting the metal, you actually get hydrogen produced instead. So the less reactive metals, things like copper continues to turn from copper ions into copper metal. If you think about the more reactive metals though, they would react with water, so something like sodium would react with water anyway. So you don't actually get sodium metal if it's in solution. You get hydrogen given off instead. So the sodium that's produced, if you like, the sodium ions, they react with the water to give off bubbles of hydrogen gas, and then that leaves behind the hydroxide ions in the solution. So that when you electrolyse sodium chloride, you get, instead of getting sodium metal, you get hydrogen gas, and you leave behind sodium hydroxide in the solution, and that is then used for other purposes as well. If you've got the halogen, then that's the halide ion, that stays and gives you off the halogen. So chloride still gives you chlorine, bromide still gives you bromine. But if you've got something else present, like a sulfate, then that instead you get oxygen given off with those ones. So if you've got sodium chloride solution, you expect to get off hydrogen gas, sodium hydroxide left in solution, and the chlorine gas given off. If you've got sodium sulfate, in that case you get the hydrogen gas and the oxygen gas, and you leave behind the sodium hydroxide. Okay.
Awesome. We're getting a lot of questions asking, what is condensation polymerization?
Ooh, condensation polymerization. Okay. Well, condensation is sort of like happens on windows. It's water produced, and the same is a bit true with condensation polymerization. So there's 2 basic sorts of polymerization. One is addition, and one is condensation. In addition polymerization, then you don't get another product formed. All the monomers join together. So I need a bit of help with this one, guys.
Yeah.
Okay. Okay, right, so we've got so we know what's happening. So we've got alkenes here. We've got a double bond in an alkene for addition polymerization. So when it polymerizes, what happens? Fantastic, and they join together, and you get a long chain formed. Okay, so that's formed with no other product. All the individual molecules, the monomers, react together. In condensation polymerization, you don't have a double bond between the 2 carbons. And so what happens is the 2 molecules join together, and in the process they give off water, or sometimes HCl. So the typical examples for that would be something that would be an alcohol and a carboxylic acid. So this molecule here is my carboxylic acid. I will quickly make an alcohol. There we go. And I've got an alcohol along the lines of that. So in condensation polymerization, what happens is these 2 groups to join together, the alcohol and the carboxylic acid bit join together. So we lose the hydrogen off that one, and we lose the OH off that one, and they join together like so to give us this ester linkage. They also produce a small molecule, and the small molecule is the water, like so. Now that's just linking the 2 molecules together. If I have condensation polymerization, I have a molecule that's got 2 carboxylic acid groups on and a molecule that's got 2 alcohol groups on normally, and that gives me my long chain. So I can quickly show that. Hopefully we're back on the screen there with that. So if I take a molecule that's got, here's my OH, there's a bit of a carbon chain in amongst like so, and then we've got my second molecule, so I've got 2 different molecules. That's really important for condensation, polymerization. Well, normally 2 different molecules from that, and then I've got a carbon, so that's my group like so, that's my group like so, like that. And what happens is that this joins onto there like so, and it also at the same time takes that one out and takes that one out, and so what I get is my linkage in the middle, which is that bit like so. So double check to make sure you've got that ester linkage. You'll have encountered that in ethylothanoate. And then over here I've got this bit over here like so. And notice that I've left that over there. I'll show you about that in 2 seconds. Let's just make that into a little box like so. Like so. So that's my repeating unit in the actual polymer. And then I put square brackets around it. Now notice 2 things. In my square brackets the bonds protrude through to show that it continues on and on. But also, if you imagine taking this bit over here and that bit over there and sort of wrapping it round and fold them together, you get your ester linkage in the middle. So the common errors that people make would be to put another oxygen in here like that, and that's wrong because then you've got 2 oxygens joined together. You see over here, you haven't got 2 oxygens joined together. So when you join them together, you've got to be able to get that linkage in the middle like so. Okay. Does that help?
Yeah. Amy says, what is the Harbour process?
Ooh, okay. I'm talking a lot. Do you want to do the Harbour process? Should I do the Harbour process? I don't mind.
We can do a team effort if you want. So the Harbour process is used to make ammonia, right?
Yeah, that's the one.
Mr. Barnes
Really
taught me
important
A-level
process.
chemistry a very long time ago. So I'm a bit nervous about getting stuff wrong. Isn't the Harbour process one that they use as an example of a dynamic equilibrium reaction? So it's kind of quite a lot of useful skills around the process itself. It's not just about making ammonia. It's about the energy involved, and kind of think about the wider applications of it.
Yeah, so it's a spot on. The memories are coming back. So the Harbour process is, as Laura says, used for making ammonia. Really important process because ammonia is the key component of making fertilisers, and without those then we wouldn't be able to grow the crops that we do. It's also an example of an equilibrium, so it has a reversible reaction, and the 2 starting products of that are nitrogen and hydrogen. The nitrogen is extracted from the air, the hydrogen is normally produced from methane, which comes from the, often actually out of the extraction of crude oil, that process. So you get the nitrogen and the hydrogen, and they combine together to give you ammonia. So the equation for that is this, so N2 plus 3 lots of H2 goes to and from 2NH3, and they're all gases that all have a gas over that. That's our equilibrium symbol in the centre there, which means that it's a reversible reaction. So the nitrogen and hydrogen, when they combine together, they do give ammonia, but the ammonia then breaks down to give nitrogen and hydrogen again. So whenever we produce ammonia, we also get the nitrogen and hydrogen present as well. In order for a company to make a profit and to make as much as possible, then they can change the conditions in order to affect that equilibrium. So the key conditions to know for this are that the pressure is 200 atmospheres, so it's quite high. The temperature has to be 450 degrees C, and then we use an iron catalyst as well for this reaction. Now the pressure is chosen because this equilibrium doesn't produce a huge amount of ammonia on its own. So it's actually a compromised temperature and a compromised pressure that we use. It's a balance of 2 things. The if we look at this equation, then it's got 4 moles of gas on this side, so it's got 1 nitrogen and 3 hydrogens there. So that's 4 moles of gas on that side. It's got 2 moles of gas on this side. So that means that if we want to push the equilibrium towards the product side, then it's going to need a high pressure. So using 200 atmospheres gives us a high pressure and it forces the equilibrium to produce more ammonia. So you might ask, why don't we use an even higher pressure? Because that would give more ammonia. Well, we don't do that because high pressure is expensive. So in order to actually have a high pressure, we've got to justify that against the yield, the amount of ammonia that we actually get. So 200 atmospheres is a compromised pressure. Any higher, it's more expensive. Any lower, it doesn't give us enough ammonia for it. The temperature is also a compromised temperature as well, because this reaction is actually exothermic for that. So this is an exothermic reaction. So if I increase the temperature on this reaction, then it will actually go back that way through them, which isn't too good. Okay, if it's exothermic in that direction, it is endothermic in the reversible direction, and so a high temperature favours the endothermic reaction, shifts it back to this side. However, by having a higher temperature, you also have a faster rate of reaction. So we use 450 degrees C in order to give us that increased rate of reaction as well.
I think maybe add in definitions of exo and endothermic. So exothermic reactions are ones that give out energy, endothermic reactions are ones that take in energy, and you know that the direction of the arrows is always the same, well, for exothermic and endothermic reactions, in terms of the relationship to the temperature of the reaction.
Yeah.
I didn't explain that very well, but
A lot of people are asking about the Chatelier principle.
Okay, well that links well to what we've just done actually. The Chatelier's principle says that a system in equilibrium will respond to try and oppose the change. You don't really have to know that bit, but you do have to know how it works, and it helps, I think, to know that it tries to oppose the change. So a good example is this particular reaction here, where if we increase the pressure, you imagine it being squeezed down, then the system responds to try and decrease the pressure on itself. So it sort of like gets in closer together. And it sort of does that by going more in the product side. So it goes from having 4 moles of gas that takes up quite a lot of space to 2 moles of gas that takes up less space. So the Chatelier's principle says that system equilibrium will respond so as to oppose the change. So in this case here, if you've got a high pressure, it will favour the side with the least number of moles. If you've got a low pressure, it will favour the side with the greatest number of moles. As far as the temperature goes, the same applies as well. So if you try and heat the reaction up by putting a high temperature in, it will make itself cooler. And it does that by going the endothermic way. So if I've got an equilibrium, like so, we've got our reactants, whatever our reactants happen to be, and our products over here. We'll do an endothermic reaction here this time now. So an endothermic is one that takes in energy. That means the delta H is positive. So it takes in energy, the energy in the system increases, that's why it's positive. And if it's endothermic in this direction, it is exothermic in this direction. So what that means is that if I was to put heat into this reaction to make it hotter, it would try and cool itself down. So it would go towards the endothermic, favour the endothermic reaction and go towards the products. If, on the other hand, I was to cool the reaction down, it would produce more heat. It would go towards the exothermic side. It is important to say, actually, that's just a way to think about it. Reactions don't feel anything and they don't decide to do anything. So when we talk about the language of it, it's important to say that a higher temperature would favour the endothermic side and produce more products.
Quite a lot of people asking about can we go through alcohols and
I was just
carboxylic
going to say
acids,
that.
and someone else talking about fermentation of ethanol. So
Okay.
you just demonstrate kind of simply with the models first, like what each of them are.
Okay. So what you have to know generally about organic chemistry is the first 4 in the sequence of each of the homologous series. So homologous series is a family of compounds that react in a similar way. They have a general formula. So something like CnH2n plus 2 would be the alkanes, and they show a general trend in physical properties. They differ from each other by a CH2. So one carbon is a methane, like so. So anything that's got one carbon in begins at meth. So if it's an alcohol, for instance, methanol. If it's a carboxylic acid, methanoic acid, it has one carbon into it. To get to the next one in the sequence, we add another carbon in. So we do that by taking the hydrogen off, putting in the next one in the sequence, and we've got the next one, such as ethane, such as this one. Again, next one in the sequence would be propane, so adding on another CH2, and like so. And then the next one in the sequence, adding on another CH2, same thing applies, would be butane. So the ending tells you what's present. If it's an ene, it's an alkene, you've got a double bond such as that one there. And same thing applies. So I can take ethene, I can take off my hydrogen there, put a CH2 group onto that one, and add in one over there, and that gets me the next one in the sequence. So it was ethane before, it's now propene, and it'll be butene if I go even further along the sequence. As far as alcohol goes, so alcohols all have an OH group in them. So this one is the very simplest one. This is methanol. Meth meaning it's got one carbon in, an tells me it's got all single bonds, and ol means we've got the OH group in like so. I can turn it into the next one in the sequence by doing a similar thing as I did before. I can take off one of those, add on that, and I get ethanol in the sequence like that. Okay, so alcohols generally, things to know about them, their general formula would be CnH2n plus 1 OH on the end of that, so they all have the OH bit into that. They differ from each other by a CH2, as I said. They are homologous series, so they have to react in a similar way. So the typical reactions they do is they all combust quite easily. They burn with quite a clean flame with that, so they react with oxygen in that way. The bigger the molecule is, like all the hydrocarbons, the smokier the flame is at the end of that, but the alcohols do burn with quite a clean flame because they've got an oxygen like so, and they produce heat when doing so. The other reactions that they undergo include a reaction with sodium. So they all react with sodium. So putting these and dropping a piece of sodium into an alcohol, you get a white precipitate and you get bubbles of hydrogen gas giving off from that. And then the other reaction for an alcohol is esterification, which involves a carboxylic acid. So carboxylic acids are very similar. So this is ethanol. This is ethanoic acid. Okay, so again, F, 2 carbons, and it's got no carbon-carbon double bonds, so it's all single bonds between there. But it has got, or would have, it would have this group here. So you've got COH there, and then a double bond to the oxygen down the bottom there. So these are the carboxylic acids. They're carboxylic acids, they're an acid. So do the normal reactions you'd expect an acid to do. And the test for carboxylic acids, you can put a bit of litmus paper in there and it would go red, probably about pH 3 or so. They're not a 3 or 4, they're not a very strong acid. But the other thing that you can react to prove it's an acid is to put some carbonate in there. If you put some sodium carbonate in there, or some sodium hydrogen carbonate, then it gives off bubbles of carbon dioxide, which you can test for with lime water going milky. But that's your test for a carboxylic acid. Now, as far as the reacting of these two together, then they react, as you saw a few moments ago, in terms of the condensation reaction. The one reaction that you have to know is called esterification. Esterification is where these two react together. So you lose the OH of the alcohol, like so, and the hydrogen of the carboxylic acid, and they join together to give you this group over here. Okay, so this is what we call an ester. That's that ester linkage that we saw before over there. They produce water as a side product as well. As far as naming this goes, then this bit here on the end is the ethyl group. So this is always the yl bit, and this bit here that's got all the O's is the ethanoate bit over there. So this one, and actually the syllabuses generally stick to ethyl ethanoate, which is a simple one here. If your syllabus mentions any others, it might mention something like methyl ethanoate, and you get that by taking off that one like so. So again, remember that this bit here, the bit without the O's, is the "-ile" bit, so methyl, ethyl, propyl, butyl, and this bit here is the O8 bit, so ethanoate as it stands currently. So this is methyl ethanoate in terms of the molecule. And these ones are they're all sort of used in things like flavourings, and they tend to be quite smelly. So ethyl ethanoate is found as the flavouring in pear drops. With that.
Yeah,
Okay.
someone in the comments, Mateen Musa, just to clarify, as Mr. Barnes just said, you probably do only need to know ethyl ethanoate, but that is the ester molecule that's made of the alcohol and the carboxylic acid. The carboxylic acid is the ethanoic acid. The ethyl ethanoate is this pear drop flavour molecule made of the two.
There's a lot of people in the comments asking if you could go through crude oil.
Oh, crude oil. Okay, yes. Right, so crude oil is the feedstock, the starting thing for almost all organic chemistry. One of the things that's in most of the syllabus is about how the crude oil is formed. So crude oil is formed from millions of years ago when little tiny sea creatures were swimming in the sea. They basically died, sank to the bottom. Over the top of it, you got piled over the rock layers over above that. The heat and pressure cooked it. The substance didn't rot because there was no oxygen there, so it turns into this crude oil mixture and some natural gas through there. Now, crude oil itself is quite a dark material, like this. Okay, if I can get it out of here. So very black, sticky, like so. It's made of a mixture of a variety of different compounds, different hydrocarbons. So first thing to say is hydrocarbon. Definition of a hydrocarbon is a substance made of hydrogen and carbon only. And that's a 2-mark definition. It's got to have the word only at the end of it. The crude oil, very thick, black, sticky stuff, not much used as it actually stands for currently. So what we have to do is to separate it. The separation procedure works on the fact that the different molecules inside here have got different sizes. Because they've got different sizes, then they've got different boiling points as well. So we use a fractional distillation tower in order to separate it. So the crude oil, which is that sort of thick liquid over there, comes into the bottom of the column, normally as a gas. So it gets heated to a high temperature first of all. So it gets turned into a gas, enters the bottom of the column, and then it rises up the column. And as it rises up the column is hotter at the bottom and it's colder at the top. So as it reaches the boiling point of each of the fractions, each of the molecules inside that, inside the crude oil, then it will then condense, and then it will turn into a liquid where it gets piped off. So the ones with the lowest boiling points, which are the smallest molecules, they come off at the top. So they tend to be gases, you sort of like things that are used for cooking gases, such as on stoves, etc. Light colour, can't obviously see anything in that, but that is basically the gas inside of there. As we go further down, we get different fractions given off. So further down, you start finding quite light liquids. They tend to be sort of like quite light coloured and not very viscous, like so. As you go further down, you start getting things like petrol, which is obviously used for cars, kerosene used for aeroplane fuel, naphtha used for chemical feedstocks, diesel, which is used for lorries and buses, tend to be more high power things. And these ones tend to be sort of like slightly thicker liquids as you go down, slightly darker colour as well. They're harder to light, so one of the properties of the fractions is that as they get bigger, so they've got the higher boiling points, they're more difficult to light. They tend to burn with a smokier flame as well. As we get down the bottom of that, we tend to get the slightly thicker liquids, which are things like the lubricating oils and the fuel oil, which powers ships. Okay, these ones darker colour, tend to be a little bit thicker like so. And then right at the bottom of the fractionating column comes off bitumen, which is a substance that's very thick. It's not much used. It's not used for a lot other than putting on roads. So you can't really do much about it. I mean, with that, so it tends to go down the roads. The problem is, for as chemists, that actually the more useful products are the ones that come out of the top, the smaller molecules with the larger. Smaller molecules that have more uses, things like the petrol, the chemical feedstocks that you use for making all the plastics and things like that. So after we've separated them out, those larger, less useful fractions, we do another process called cracking. And what cracking does is it takes the very large molecules and split them into smaller molecules. And those smaller molecules are more useful, so we can sell them straight on and use them for different products. But as well as being smaller molecules, some of those molecules are actually alkenes, which have the double bond in them. And so those are also very useful as well, because those are things we can make plastics out of.
There's a few people in here asking about condensation, polymerization again. If you, after the end of the stream, flip back to near the start, Mr. Barnes gives a very comprehensive explanation of that. Someone here asking about graphite and diamond. That's probably a good thing to go through.
Yeah.
Mm-hmm. Okay.
So graphite and diamond are both giant covalent structures, and both made of carbon, but I think knowing the differences between the two is a very sure bet for your paper. Hopefully, if it hasn't already come up in a previous paper, it probably depends on which exam board you're doing.
Yeah.
So yeah, getting the differences in properties nailed. So in graphite, the carbon is bonded to 3 other carbons in kind of planar, flat shape. But in diamond, I think Mr. Barnes will show you now. The carbon is bonded to 4 other carbons. Yeah, as you can see. So what that means is that in graphite, you've got a spare electron called a delocalized electron, which can move between the different layers of the graphite, which explains a lot of the properties. So graphite can conduct electricity, same as a lot of metals can. Also means that the layers can slide over each other, meaning that it can be used as a lubricant. Whereas in diamond, there's no free electrons, so the structure's a lot harder, can't conduct electricity. I don't know what else is likely to be on the syllabus, but...
Yeah, so basically, as Laura says, it goes back to these key concepts that the structure and bonding are really important to everything that we do. So we mentioned before about the ionic structures of metal, non-metal. Well, if you've got 2 non-metals, then you've got covalent bonding. They share electrons with that. And covalent bonding, so the non-metals, come into 2 parts. One of them is a simple molecular, and the other one is the giant covalent. And in the giant covalent sections, those that you've got covalent bonds, which are very strong, and you've got lots of the bonds you have to break. So they have got very high melting and boiling points, and that's how you tell the giant structure from the simple structure, because you've got to break many strong bonds. Those are your 2 key words, the many and the strong bonds that come through. Laura's talked about the properties of them, and that covers that off. You have to be able to recognise them through that. That's probably the only other thing. So diamond, not very good at drawing diamond. Diamond basically sort of like
I love this bit, yeah.
comes out along the lines of that. You've got your carbon atoms there. One comes out behind. So that's our bit that looks like that, like so. And then all you do when it comes, you're more likely to recognise and actually has to draw it. But then you just repeat that. So you just come down, you come down, you come down, and then you come out, you come behind, like so, out to the front, and you just sort of join these bits together like that. Okay, so it looks in that type of structure. Whereas graphite consists of hexagons, and as Laura says, it's a layers of hexagons, like so. So each one of them has got 3 bonds, like so. There we are. Okay, and then that's not very good drawing, but anyway, it'll do. And then you have got another layer underneath here, like so. So D, 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 D.
I think an important thing to remember is don't just think of these structures as abstract concepts. Think about how the structure relates to the properties of the substance. Otherwise, it's, I think, harder to get your head around if it's just, completely abstract.
Yeah. So Laura mentioned the idea about 4 bonds. So 4 bonds, carbon's got 4 electrons. Which means that each one of those electrons is in one of these 4 bonds over here. Okay, so a covalent bond is defined as being a shared pair of electrons. 2 marks for that. 1 for the sharing electrons, 1 for the pair of electrons.
Very good segue into something that a lot of the people are asking about, is the different types of bondings.
Okay.
Yeah.
Well, this is quite a good example of explaining it, really, because we've got our covalent bonds here, which always occurs between 2 non-metals. That's the sharing of electrons, which is normally sort of drawn like that, where you've got 1 electron from each one. We'll do a better diagram in a minute maybe with that. But that's your strong covalent bonds, and they tend to be required. If you've got a molecule that's got lots of those bonds in and it's covalent bonds, then they're going to be very strong and require high melting and boiling points. And Laura mentioned about graphite being layers that can slip and slide. And so in graphite, you've only got 3 bonds. You've got 1 electron left over, which is a delocalized electron and can move between the layers, which gives you the conduction. It also gives rise to, you've also got between them, you've got these weak intermolecular forces. And the weak intermolecular forces are easily broken, so the molecules themselves will slide over one another like that. Should we do more on bonding?
Yeah, so
Okay.
I think
there's a lot of
ionic
people
bonding and
asking
palette
about
bonding
bonding.
as well.
Okay, so switch to clean board. Right, okay, so let's carry on with covalent bonding because that's where we got up to with that. So there's 3 types of bonding that you've got to do. You've got ionic bonding, covalent bonding, metallic bonding. Covalent bonding occurs between non-metals only. So you've got 2 non-metals like hydrogen made up of 2 hydrogen atoms. That would be covalent bonding. If you've got something like carbon, again, they're joined together, 2 non-metals. That's that carbon-hydrogen. They're all covalent bonds. So they share electrons. So if I take the simplest one, the hydrogen, then I would have a hydrogen atom like so, and a hydrogen atom like so. Hydrogen has got 1 electron, and so I've got 1 electron in that first shell. So you have to know that the first shell is full with 2 electrons, and the whole idea behind this is that we're trying to get full shells, and that's a stable configuration. Think of the noble gases. All the noble gases at the end of the periodic table have got full outer shells. So the way you can get a full outer shell is you can either pinch electrons or take them from something or lose them to something else, or you can share them. And if we've got 2 non-metals, they share electrons. So the hydrogen shares electrons, and those 2 hydrogen atoms are actually found together as a hydrogen molecule. Here's a hydrogen molecule. The electrons are between the 2, like so, and here each hydrogen has now got a full outer shell because it takes 2 electrons to fill an outer shell, and the hydrogen's stable like so. That's the basic covalent bonds. It works for lots of other things. We can do carbon-hydrogen. So if I take a carbon over here like so, and was to draw a carbon atom, so carbon has got 2 electrons on the outer shell like so, and it's got 4 on the inner one like that. That means it's got 4 spaces that have to be filled. And because it's a non-metal, if it reacts with hydrogen, then it will share electrons. So we end up with a methane molecule that looks like this. I might need to do my diagrams bigger. Are my diagrams okay over there?
Yeah, fine.
I think if anybody would like to see this, go over these molecules, there's plenty of examples on stuff like BBC Bioslides.
Yes.
Showing.
Yes, there is.
Yeah, definitely.
So this is why carbon reacts with 4 hydrogens in order to give me methane, like so. So the key thing is the electrons are there shared in between. Probably ought to mention oxygen at the same time, because if I take an oxygen atom, then oxygen is in group 6, so it's got 6 electrons in the outer shell, like so. So there's 6 electrons. I put them singly first of all, and then I put 2 doubles like so. Now that means that the oxygen needs to gain 2 electrons in order to have a full outer shell of 8, because it's got 2 in the inner ones and it's got 6 on the outer ones like so. So if I take another oxygen like this, so here's my other oxygen, same thing again. It's called a dot and cross diagram because I'm using dots and crosses for it, like that. And then when these react together, they're found as a diatomic molecule. So what happens is these bits here have to share electrons. So to get 8 electrons, you've got to think, okay, I've got to share 2 electrons. So that means that the starting point is to have the 2 electrons from each oxygen being in the middle. Then I put my there's my oxygen like so. I can put 2 electrons over there, 2 electrons over there. So this oxygen has got its 6 electrons, 1, 2, 3, 4, 5, 6, and it's shared 2 from this oxygen, so it's now got 8, which is a full outer shell and stable. Whereas over here, again, this one has got its 6 electrons of its own, but it's also got the 2 it's shared over here, so they're both stable. I've not drawn the ring around it just to make it a bit clearer for this one, but you could just draw a ring around it like so. So non-metals always bond by covalent bonding. If I take a metal and a non-metal, then they bond by ionic bonding. So if I take the simple example would be something like sodium chloride, that's the common example. So sodium is in group 1, that means it's got 1 electron in the outer shell. So if I take a sodium atom like so, it's got an electron like that. So to get a full outer shell, it can either gain 7 in order to get 8 in the outer shell, or it can lose 1. Well, it loses 1 through that. So what we end up with is a sodium ion like so. It's got no electrons in its outer shell, but it's lost an electron. Now when it loses an electron is negatively charged. So it's lost an electron, so what's left behind is a positive ion. Because it's had here, sodium's got an atomic number of 11, so it had 11 protons and 11 electrons, which made it neutral. Over here, it's still got its 11 protons, the protons never change, but it's now only got 10 electrons. It's got 1 extra proton, 1 extra positive charge. If I take a chlorine, then chlorine is in group 7, and again I'll just do the outer shell. Group 7 means it's got 7 electrons on the outer shell, so it's got like so. There's its 7 electrons, like that. I should have already used dots, but I'll use a different colour maybe with that. So that's my chlorine atom. Now when it forms an ion, it gets to a full outer shell. It gets to a full outer shell, it's got a choice. It can lose 7 or gain 1. It's going to gain 1. So I end up with my chloride ion. Notice the name ending changes like so. It's got the 7 electrons it had before, but it's also got another electron that it's got from somewhere. Well, where does it get it from? Well, often it gets it from the metal it's reacted with. So the sodium atom here became a sodium ion. It lost an electron. Where did the electron go? The electron went to the chlorine to form a chloride ion. It's now got an extra electron, so it's now got a negative charge like so. So that's the formation of the 2 ions. And the ionic bond is simply the attraction between the positive ion and the negative ion. It's an electrostatic attraction between 2 oppositely charged ions. And they attract together in what's called an ionic lattice. So in an ionic lattice, what happens is if I take my positive ion like so, which one I take, and a negative ion, they'll attract each other together. But that negative ion will also attract a positive ion over there, and a positive ion over there, and a positive ion over there. And they'll attract a negative ion, and a negative ion, and a negative ion, and a negative ion. And that's be the pattern that we actually get, like so. And that's in 2 dimensions, but of course it carries on in 3 dimensions as well. It goes out over there. And that's called an ionic lattice. So substances that are metals and non-metals, ionic bonding, have high melting points because in order to melt them you have to separate out those ions. So that requires breaking the ionic bond, which is a very strong bond, but it also involves maybe breaking lots of bonds because the structure goes on and on and on in 3 dimensions. That's ionic bonding. Should we talk simple molecular bonding? Should we talk about simple
maybe we
molecular
go through it
forces?
really quickly.
Really quickly.
Anyone who's complaining about this being paper 1 content, we're just responding to what we've been asked in the comments because everyone's specifications is obviously different. So do bear with us and let us know in the comments like what else you would like us to go through.
I should say that the syllabuses are based on key ideas. So in terms of the actual paper itself, they're not going to they're almost unlikely to ask anything about paper 1 detail, but key ideas, and both all the syllabuses generally have these key ideas, might want you to just recognise the fact that things are ionic or covalent just a little bit without going into detail.
Like chemistry is literally all about bonds and energy when it comes down to it.
So we're doing the main bits.
It's not going to do you any harm making sure all this stuff is solid in your minds.
There's also a lot of people asking about mole calculations, so we might want to do an example maybe.
Okay, so mole calculations. There are 3 equations, well 4 equations I suppose, that you actually need to know in order to do that, and it's worthwhile making sure that you know those. And if somebody might end up forgetting them, then when you open the exam paper, you might want to go and just write it inside on the front cover of the exam paper or something, and that way you can really refer back to it.
Yeah, definitely.
If you're dealing with masses of things, so generally we're talking about solids, but could be liquids again, then the equation you need to have is that moles equals the mass over the Mr. You might call it RMM, it's the same thing through that. Okay, so moles equals mass of Mr. If you're dealing with solutions, then you need to know that moles equals volume times concentration. And really important to note that the volume here needs to be in decimeter cubed. So the decimeter cubed, you take your centimeter cubed and you divide it by 1,000 to get that. And then the other equation that's in some of the syllabuses, don't know whether it's in all of them, okay, is that the moles of a gas equals the volume of the gas, and again that's got to be in decimeters cubed divided by 24. You might see it volume in centimetre cubed divided by 24,000. It's the same thing, it works out the same way, so it depends on what you want to do. The other equation that may come up that's worth knowing about is the number of atoms. So the number of atoms, or the number of particles, equals the moles times the Avogadro constant, okay, which is sometimes given the L. It'll be given in the question, but it's 6.023 times 10 to the 23 from that. So those are the ones you know. So if you've got your phone out and you don't know them, take a picture on the screen if it's up on the screen, and that way you remember it as we go through.
You say that it's about 20% of the marks on the paper are likely to be on calculation, so if you can get this stuff really solid in your mind, then you can sort of guarantee yourself 20% of the marks on the paper, which is, we'd all like.
Yes.
Yeah, definitely.
So do you want an example of a question on moles then, through then?
Let's just have a quick look, see what else people are asking about. Amar is saying, can you go through ways of extracting phosphorus to make fertilizers?
There's a few people saying they're a bit stuck on distillation and fractional distillation as well.
We did do fractional distillation
Before.
a little earlier in the stream, so maybe just wait till the end of the video and skip back for that.
Yeah, there's some really good animations as well.
Yeah.
In terms of that, I mean, so the key thing is separate it on boiling points. The column is hotter at the bottom, cooler at the top. The fractions rise up, and then they separate according to boiling point. So the larger molecules come off at the bottom; they've got the higher boiling point. The smaller molecules off at the top, they've got the lower boiling point because of that. The phosphate rock to make fertilisers with that. There's not a lot of detail on this, but the phosphate rock is basically treated with either nitric or sulfuric acid, and that gives you your fertiliser. So I'm not sure what else we want to add. So I don't
know. Let us know in the comments if there's anything in particular
definitely.
you're struggling with.
I mean, one of the things with the salts, I suppose, is to say that you sort of knowing that nitric acid always produces a nitrate, sulfuric acid always produces a sulfate, and phosphoric acid always produces a phosphate. So,
yeah, good tip.
Definitely.
A few people asking about ion tests.
Yeah.
okay. So paper 2 does include the qualitative analysis tests for that. So that means that, and they are easy marks because there's certain bits really easy marks. Yeah, certain bits that you sort of just have to learn, and those are your sort of definite marks for things like that. So knowing that the test for carbon dioxide is lime water goes from colourless to milky. Test for oxygen relights a glowing splint. Test for hydrogen gives you a squeaky pot with a lit splint. For that, chlorine bleaches damp red litmus paper. Goes with red first of all, then it bleaches it white through that. And then you've got your ion tests as well. So some things you can test for by flame ionisation, basically flame tests like so. So the ones that are in the syllabus generally are lithium, which gives you a sort of scarlet, calcium gives you a brick red, potassium gives you a lilac, sodium gives you a yellow, copper gives you a green. Those are basically the 5 ones that are there. The other way for testing for positive ions, for metal ions, is adding sodium hydroxide. And when you add sodium hydroxide, you get a precipitate. So adding a bit of sodium hydroxide to a solution containing calcium, magnesium or aluminium, that gives you a white precipitate of the hydroxide. So calcium gives you calcium hydroxide, and magnesium gives you magnesium hydroxide, and aluminium gives you aluminium hydroxide to begin with. Now all those are white, and the way to remember that is that they're all in the S block. They're not in that centre block of the periodic table, not in the transition metal section. So that gives you a white precipitate. How do you distinguish them between those three? Well, the calcium and the magnesium you can distinguish by using the flame test, because the calcium gives you the brick red colour. The aluminium will dissolve in sodium hydroxide if it's in excess. So when you first add the sodium hydroxide to it, give you a white precipitate, and then it dissolves to give you a colourless solution after that. The transition metals that you have to test for, so that centre block of the periodic table, the common ones you get for that are copper. So copper gives you a blue precipitate of copper hydroxide, and then the two ions, and they're iron 2 and iron 3. And you have to be really clear when you're talking about any part of iron in an answer. If it's the ion form of iron, refer to whether it's iron 2 or iron 3. So iron 2 gives you a green precipitate, and iron 3 is a brown precipitate. So the way to remember it is that iron 3 is always rust. So iron 3 is the rusty one, that's the more stable form. So brown precipitate of iron 3 hydroxide. The iron 2 hydroxide gives you a green precipitate, and then over time it slowly gives you a bit of brown on top because it gets oxidised by the air to iron 3.
Okay.
Anions? Do anions?
Quickly.
Okay. So the anion test, so carbonate is reacting with an acid that gives you off carbon dioxide. I already mentioned the carbonate test earlier. Sulfate test is to add barium chloride. Adding barium chloride to it gives you a white precipitate of barium sulfate. And finally the halides. So these are the halides, not the halogens. We're talking about chloride, not chlorine. So chloride, bromide and iodide are all tested for by silver nitrate and nitric acid. You've got to have the nitric acid so you don't get a white precipitate of a carbonate formed. But with the silver nitrate you get a white precipitate with the chloride, and that precipitate is silver chloride. You get a cream precipitate with a bromide, and that's silver bromide, and you get a yellow precipitate of iodide for that. And you have to know the ionic equations for those reactions.
Okay. I think we're going to wrap up pretty soon. Mick, at the end of the stream, watch back a bit earlier on, Mr. Barnes explains a lot about an equilibrium in the context of the Haber process then.
Definitely.
And Finn McGuinness, we did some stuff on the organic chemistry earlier in the live stream as well, so if you want to skip back for that, that would be great.
Yeah. I've got a question here, I'm just scrolling up through the comments, that says, have you got any tips for us in order to get a 9?
Okay. Know everything. Again, but bringing back to the starting point really is that be really clear in your answers. So where possible, use an equation. Make sure you start off with the obvious points first of all, so that if you're trying to explain something, don't just jump into the final bit that's there in the answer. Think about if you had to explain it to somebody very simply, what would be the starting point in your explanation? One of the big bits in the papers is probably going to be the practical, based on the core practicals as well. So from that point of view, make sure that you've looked at the core practicals and that you think through carefully what the question's asking for.
On the core practicals, I said this in a stream the other night on a biology thing, don't think of the core practicals as being a bit of the syllabus to learn in their own right. They're there to explain concepts that are in the rest of the syllabus, and you're likely to be asked questions around the core practical that are about the theory. Don't just learn an experiment without realising how it fits into the rest of the syllabus.
Yeah, definitely.
So something like the thiosulfate, the rates of reaction, the thiosulfate experiment through that. So you have to know, you don't necessarily have to know exactly how the experiment works, but you have to be able to interpret it based on the information given. So the concepts there might be things like a fair test, so which variables do you control and which ones do you change. So in the thiosulfate test, then normally you're talking rate of reaction, so the things you've got to keep the same or change would be concentration, temperature, depending on which variable you're trying to investigate. So your practical has to be based around trying to do that.
Have you got any very last minute tips for anyone ahead of tomorrow's exam, kind of what last minute revision or any last minute preparations?
At this stage, calculations are hopefully okay, because sort of calculations you learn by doing lots of practice and practice and practice with those. But as far as questions with calculations go, if in doubt, convert to moles. Right? That's my guiding principle. Look at the question and see what information is given for you. If it's given you a mass, then you're going to have to convert it to moles, because you can't use any other equations for that. If you've got solutions, you've got to use the moles equals volume times concentration, because that's in there. Be careful about units. For that, converting into centimetre cube, decimetre cube, bound to be something upon that. If you've got to think about core practicals, just have a look at the ones that are particularly in paper 2. So that's the rate of reaction ones. Make sure you can draw lines of tangents, because they're all things that's like hopefully a skill. So you're sort of like hopefully aware of those by now, but just check you do that. The bit on the night before is more making sure you've learnt those key facts. And so probably have a look at your syllabus, because the syllabus is in quite a lot of detail. The syllabus actually tell you the basics of what you really need to know. So if you haven't looked at it already, have a look at that by all means, because you'll be able to tick off certain things that are there with that. And then other than that, if you're feeling pretty confident, particularly sort of that's someone asking about being on a 9, things like that. If you haven't had a look at them already, maybe have a look at the examiner's feedback. So when you go onto the websites, I know that Edexcel do this, I think AQA do a similar thing as well, that you get 3 things for each paper. You get the paper itself for past papers, you get the mark scheme, but you get the examiner's feedback, and that's really important because they show you alternative answers, and you can also see how answers are credited and how they're not. So you can see why an answer was worth 1 mark rather than being worth 2 marks. If you're really trying to get those top grades, then definitely have a look at that examiner's feedback.
Yeah, that's really good feedback.
Definitely.
And yeah, manage your time in the exam. That's always a good tip. Think about how many minutes you've got per mark that you've got to earn, and if you've got a 6-mark question and you're there for, much more than that, you need to be moving on. And yeah, just get a good night's sleep. I think it's a morning exam, so don't stay up till 2 in the morning revising. Do what you can and then go to bed at a sensible time, and read the questions in the exam.
I think definitely.
And then to go back and just make sure that your answers match the question asked. With that, we started off the session by saying, didn't we?
Yeah, exactly.
Yeah.
Well, I think that's it for the live stream, guys. So thank you for getting your questions in. Thank you, Mr. Barnes, for joining us, and thank you, Laura.
Thanks.
Good luck to everyone doing exams this week. It's the final stretch, and good luck to everyone doing chemistry especially. See you soon. Bye.
Good luck.